Hello and welcome to the lecture number 19 of Physics 401A. In this lecture, we start a new topic of perturbation theory for ordinary differential equations. In mathematics, perturbation theory is an approximate method of solving an algebraic equation, a transcendental equation, a differential equation, okay, only when the given equation is slightly deviated from another equation which we know how to solve exactly. So it does not say that we never know how to solve the perturbed version exactly. It simply says that we only have to know always how to solve the unperturbed version exactly. If we know how to solve the perturbed version exactly, that's even good. We can check how the perturbation method can give us approximative solutions, okay, and realistic solutions, of course. And if we don't know, then we have to trust on the method, and we can actually cross check by other physical considerations, okay. Now now the thing is that here in this discussion we start from very basic algebraic equations. The reason is that algebraic equations are easier to solve, and I will start from a very basic quadratic equation which you also know how to solve exactly, okay, and how to solve exactly both the perturbed and the unperturbed version. That's something very interesting, and now we can cross check whether really the perturbation method works or not, okay. Now let us first have a look to this equation. X squared is equal to 1. We all know that some of you would say that I will solve this equation just by taking the square root of 1 and then by saying that it is plus minus 1, and then some of you will say that I will just take this 1 to the left hand side and I will factorize this. X square minus 1 is equal to 0, so x plus 1 into x minus 1 will be equal to 0, then x can be plus 1 or minus 1, okay. So up to this we don't have any problem to solve it exactly, we know. Now if we just give you another equation which is x square is equal to 1 minus 0.02x. Now this x is multiplied to a coefficient which is very small with respect to 1, okay. So this equation basically deviates from this equation x square minus 1 is equal to 0 by a very small quantity, okay, and that's why we can think of applying the perturbation method, okay. But it is also true that given this equation is a quadratic equation, we also know, irrespective of the value of epsilon, whether it is big or small or whatever, we know for quadratic equations to solve directly. So that we will exploit here, okay. So the quadratic equation is x square plus 0.02x minus 1 is equal to 0, and then the solutions will be simply minus 0.02 plus minus root over 0.02 whole square plus 4 by 2, okay. If you calculate this in the normal calculators, you will have this result. So minus 0.01 plus minus 1.0000, and after that 4999875. This is within the precision of the calculator. If you can use much more powerful calculators or computers, you can have much more precision, okay. Now what will be the values of x? The roots of x. X will be simply then 0.99004999875 and 1.01004999875. So if you now take, okay, at best the result correctly up to 3 decimal places, it will simply give you 0.99, because 3 decimal places means 49 will be rounded off by 5 over here. So in the 4th decimal place you will have 1, but that is finally will not play any role. So finally up to 3 decimal place you will have the answer rounded off to be 0.99, and the same thing will be over here. You will have 1.01, okay. Now that much we can do here directly. and so that is the exact solutions. So here for this case, we know the exact solutions both for the unperturbed and perturbed version. Okay. Now, our question is that can we find the solutions otherwise? Okay. In order to do that, let us first have a look that what can we do even in this process of direct solution for the special cases where we have a very small epsilon. Okay, so we will use this method, but we will now use the property of epsilon. Okay, that means that 0.02, okay, which I can call as a small parameter. Okay, epsilon or epsilon prime, maybe I have called over here. Okay, epsilon prime. Okay, then I will just check which type of property this can have, okay, of the this direct solution can have for an arbitrarily small epsilon prime. I will of course apply the same solutions over here. Okay, so x will be equal to, then this is also another quadratic equation, x will be minus epsilon prime plus minus root over epsilon prime square plus 4 by 2. Okay, now I use the property that epsilon is very small with respect to 1, and then finally you can do this type of expansion. So you have finally one form. So minus epsilon prime by 2 will be the first term which comes from this one, and then the second one will be plus minus 1 plus epsilon prime square by 4 to the half. Then expanding this in a series, you can easily write this type of series, which will be a series in not epsilon but epsilon prime square. Okay, so finally you will have this equation as minus epsilon plus minus 1 plus half epsilon square minus epsilon to the 4 by 8 plus the higher order terms. Okay, now if we just keep the first order of epsilon, I mean up to the first order of epsilon, then we will see the two roots of x will be plus minus 1 minus epsilon prime by 2, which are nothing but 0.99 and minus 0.1.01. So exactly matching with this one. Okay, so here I have done a mistake just for your information. Here it should have a minus sign because it's minus 0.01 minus 1, so it should have a minus over here. So please write a minus over here, and so this will be minus 1.01. Okay, and that we will recover over here. Okay, these two equations. I give you a small home task just by saying that can you check for the order up to epsilon square, and actually if you are enthusiastic you can check for the higher orders, and you will check whether step by step you are converging towards these two solutions. Okay, once again this will be a minus 1.01. Okay, but that was the general formulation. We have not used the perturbation method. What is the classical method of perturbation? That we have not used. Now we will try to learn, we will learn how to use that. Let us now take the idea that the solution of the perturbed equation is very close to that of the unperturbed one. So which equation is the unperturbed one? The equation x square minus 1 is equal to 0. That is the base equation. And that is very necessary, and that is actually essential that we know the exact solution of that unperturbed version. Okay, whether we know how to solve exactly the perturbed version or not, that is not necessary, but the unperturbed version must be solved exactly. Okay, so very close to this unperturbed one, the perturbed version, only if the perturbation is very small. That is very small with respect to 1. That is our terminology we will use throughout. And also the solution of the perturbed equation deviates from that of the unperturbed equation by a power series of the smallness parameter epsilon. Okay, so we have two considerations. The first one is that the perturbed version just deviates from the unperturbed version by a very small contribution, very small term. For us this is epsilon prime, that was epsilon prime times x, and or rather minus epsilon primes times x, okay, times x, or you can take any other type of thing. You can actually say epsilon prime is your 2 times epsilon, but you can take now epsilon as 0.01 instead of 0.02. That is the same thing, because 0.02 and 0.01, they are of the same order. Okay, so that you can do. Okay, and then you can again consider this deviation to be small with respect to the unperturbed one. The second consideration is that if this is like if this part is valid, then the solution of the perturbed equation deviates from that of the unperturbed equation by a power series of the smallness parameter epsilon. Okay. Now, this is not a, very correct. This is not a very correct statement, because so it's a power series of the smallness parameter epsilon, but the power series starts from epsilon to the power 1. The epsilon to the power 0 basically gives the solution, or rather should give the solution of the unperturbed version. Okay, so just keep it in mind here when I say that it will be giving the power, the solution of the perturbed version will be given by a the solution of the perturbed version just deviates from that of the unperturbed version by a power series of the smallness parameter epsilon. You have to keep in mind that it should start from epsilon to the power 1, because the zeroth order solution is already the unperturbed one. So the perturbed solution is exactly equal to the unperturbed one plus the other terms starting from epsilon to the power 1. Okay. Now the question is that whether this is a guarantee. Well, there is no mathematical rigorous proof for that. We do not know whether for an arbitrary form of equation this actually works or not, but we just assume that to proceed. So this type of thing is called an Ansatz. Ansatz is a German word which is basically meaning the primary approximation. Okay, which doesn't have any proof, but it comes out of intuition. Okay. Now assume that we do not know how to solve quadratic equation. Okay. Now we don't know how to solve in general ax squared plus bx plus c is equal to 0, this type of equation. But somehow we know that what is the solution of x squared is equal to 1. Let's say you take the square root, or just for that special case you could factorize efficiently, or you will come out with exact solutions plus minus 1. Okay. Now we can say that we assume the solution of the perturbed equation is of the form x of epsilon will be equal to x0 to the power x0 times epsilon to the power 0, and that is the unperturbed solution. Okay, so x minus x0 will now be a power series of epsilon starting from epsilon to the power 1. You will see, and that will simply be given by x1 epsilon plus x2 epsilon square up to infinity. Okay. So first of all, we have to assume here that this type of series exists, and as n tends to infinity, you can write that as a summation over xn times epsilon to the power n ranging from 0 to infinity, and the assumption is this series exists and converges to the original solution, the real solution of the perturbed equation when n tends to infinity. Once again, there is no proof for that. Okay, we just assume. Now let's apply this for our trial solution. So this is an applied approximative mathematical methods. Okay, so there should not be actually any rigorous proof. These parts are coming out of our everyday application of mathematics. Okay, or mathematical methods. Okay, so now we put our trial solution to this original equation. Okay, and that equation will now be x0 plus x1 epsilon plus x2 epsilon square up to infinity square plus 2 epsilon times again the total series minus 1 is equal to 0. Okay, so now we can write this as a polynomial, the total thing as a polynomial of epsilon. Now you know, when you have a polynomial of a constant quantity, okay, whose is equal to being equal to 0, then you know that every power of that polynomial constitutes an element of the basis of the solution, of the polynomial. Okay, and finally, each of them should be as they are constituting a basis. Finally, one of them can vary, being independent of the other. So, if the whole thing to be is equal to 0, so you can think that every single coefficient of every coefficient of the all the coefficients corresponding to the powers, the individual powers of epsilon, that means epsilon to the power 0, epsilon to the power 1, epsilon to the power 2 will separately vanish. Okay, it's like a vector, okay, whose all components should be 0 when this is equal to a null vector. Okay, as simple as that. Now, for the above relation to be valid for an arbitrary value of epsilon, well, that is another way of writing, of course. The individual coefficients of epsilon n should vanish for all n. And then for epsilon to the 0 contribution, the coefficient of the term of epsilon to the 0 gives us x0 square minus 1 is equal to 0. And that's exactly our unperturbed equation. So this is the first thing you can verify, okay, that whether the 0th order coefficient would give you back the unperturbed equation or not. If not, there is a problem in your calculation, okay, because this is the very primary requirement. Okay, then for epsilon to the 1, we have the coefficients 2x0 x1 plus 2x0 is equal to 0, and for epsilon square we have x1 square plus 2x0 x2 plus 2x1 is equal to 0. Okay, now from this one you can know the exact solution of the unperturbed equation. From this one, now you know x0 can have two values, but if you just can see this second equation, it simply says that x0 times 1 plus x1 will be equal to 0. We know none of the solutions of x0 is 0, so we can basically say 1 plus x1 should be equal to 0, so x1 will be minus 1. So although x0 has two possible roots, x1 only have one possible root. But x2 then will be equal to, if you just put back the values of x0 and x1, you will see that x2 will have the value 1 by 2x0, so it will also have two values depending on whether x0 is plus or minus 1. Now, if you just put those values over here, you will see just up to taking the contributions of epsilon square, so you will see now you have this equation over here, this equation. Okay, so this equation will now be equal to x epsilon will be equal to 1, so x0 is minus 1, so it will be minus epsilon plus, so I take for the time for this case x2 is equal to plus half, so it will be plus half epsilon square, and when x2 will be equal to minus half, this will be minus half epsilon square. Okay, because finally it will be x2 epsilon square over here, so plus minus, so finally I will have two roots possible. Okay, again if you just now take this subpart, you will see these are giving me 1 minus epsilon and minus 1 minus epsilon. So 1 minus epsilon and minus 1 minus epsilon, they are just here. Okay, so we exactly agree up to first order, we can see with this direct solution method for small epsilon. Right, now your task will be to check for the terms up to epsilon square, whether it also matches with this direct method over here. Okay, so for that you have to go up to this and you have to check, and actually you can check easily, because you will see here you will have 1 plus epsilon square, 1 plus half epsilon square and 1 minus half epsilon square, and that's exactly what you will have over here. Okay, so now your real home task will be to check the coefficients of epsilon cube and epsilon to the power 4. Okay, and you can have you can note that here basically there was no term of epsilon cube here. Okay, after epsilon square it was epsilon to the 4. Okay, so just check that and let me know whether everything goes okay or not. Okay, and you will see that when you are just going up to higher and higher orders of epsilon, or rather epsilon, you will see that your equation, or your solutions, approximate solutions, will be more and more close to these versions. Okay, so that is the power of valid perturbation method. If the perturbation method really works, then you will have this type of scenario, and that you can cross check by doing. Okay, there is no other recipe. You do it and you cross check. Okay, so here we saw that the perturbation method works just by assuming the solution of the perturbed equation as a power series of the perturbation parameter or smallness parameter, sometimes we call epsilon. Okay, of epsilon. Okay, so here you can see that in this process, if you just can see that here in this process, I just took so once again, so I took epsilon prime as 0.02 and epsilon as 0.01. So these are two parameters. So here the whole calculation is done in terms of epsilon. Okay, you can do the whole thing in terms of epsilon prime, no change will be there. Okay, this method is called the method of regular perturbation theory, where you just take where you just write the solution of the perturbed equation directly as a as a power series of the perturbation parameter epsilon. Okay, regular perturbation theory, or we will call it RPT. Okay, now two things to remember. Although it looks good that this works, but if the smallness parameter is associated with the highest order, okay, that means if instead of x square minus 1 minus so x square minus 1 is equal to minus epsilon prime x, we had epsilon prime x square minus 1 is equal to x or minus x, then it would not have been it would not be a great idea to use the regular perturbation theory. Okay, and that is the part of that is the domain where you can use singular perturbation theory. Okay, that is beyond the interest of our course, but we can, if you are interested, you can go through that independently. Now the second point to remember is that the equation where the dominating terms do not balance each other asymptotically as epsilon tends to 0, that you have to understand what it means. Okay, so as epsilon tends to 0, for example in this equation, okay, so as epsilon tends to 0, you have x square minus 1 is equal to 0. So you know that x has a solution of plus minus 1. So basically roughly x square and 1 both are of the same order, you know. Okay, if this is not true, then the application of RPT is not a good idea. Okay, we will see with a concrete example that in the tutorial, but then we can assume still a power series which will be a function, special function of, not a special function, a function of epsilon, but not the epsilon itself. Okay, so and after this, so this was all about the perturbation theory for algebraic equations. In the next part, we will start discussing the perturbation theory for differential equations. Okay, thank you very much.